Ground fault circuit interrupters, or GFCIs, operate by monitoring the current flowing through the hot and neutral conductors. The GFCI is designed to detect any imbalance in the current flow. When the current flowing out on the hot conductor does not equal the current flowing back on the neutral conductor, the GFCI recognizes this difference as a potential ground fault. This imbalance signifies that some current is leaking to ground, meaning it's taking an unintended path back to the source rather than returning through the neutral wire. The test button on a GFCI breaker simulates a ground fault condition by creating an intentional imbalance in the current flow. When pressed, the test button forces a small amount of current to bypass the neutral conductor and flow through a resistor within the breaker itself. This intentional diversion of current creates the necessary imbalance that the GFCI is designed to detect. Upon sensing this imbalance, the GFCI breaker trips, interrupting the circuit and cutting off power. This trip in action confirms that the GFCI is functional and capable of responding to a ground fault. In contrast, a load test involves connecting an electrical device or appliance to the circuit and energizing it. During a load test, current flows through the connected device and returns to the source through the neutral conductor. If there is no ground fault present, the current flowing out in the hot conductor will be equal to the current flowing back on the neutral conductor. In this scenario, the GFCI will not detect any imbalance and will not trip the breaker. The GFCI breaker only trips when it detects a difference between the outgoing and incoming current, indicating a ground fault condition. When the test button is pressed, the current is deliberately forced to flow through a resistor built into the breaker. This creates an imbalance, causing the breaker to trip regardless of whether there is an actual load on the circuit. The test button serves as a means of verifying the GFCI's functionality by simulating a ground fault. The absence of a bond between the neutral and ground bars can lead to a situation where the neutral and ground conductors are at different electrical potentials. This potential difference arises due to various factors, including transformer phase shifts and impedance differences in the wiring. When the neutral and ground conductors are at different potentials, it can create unwanted current flow through the ground conductor. This unintended current flow can interfere with the proper operation of GFCIs, leading to nuisance tripping. Nuisance tripping occurs when the GFCI breaker trips even though there is no actual ground fault present. By bonding the neutral to ground, the electrical potential difference between these two conductors is eliminated. This ensures that the neutral and ground conductors are at the same potential, preventing unwanted current flow and minimizing the risk of nuisance tripping. Bonding the neutral to ground is a crucial safety measure that helps maintain the integrity and reliability of GFCI protection. To elaborate further on the importance of understanding GFCI operation, let's consider the specific scenario where a facility discovered several circuits failing the GFCI test. These circuits originated from the same 208.120 volts alternating current panel, which was supplied by a 480 delta to 208.120 volts transformer. Upon inspection, it was found that there was no bond between the neutral and ground bars in the panel. This lack of bonding was a significant concern because it directly affected the proper functioning of the GFCIs. The tests were conducted using a handheld device, and the circuits were protected by GFCI breakers in the panel. While the test button on each breaker tripped the circuit as expected, indicating that the GFCI mechanism itself was functional, the load tests were failing. This discrepancy between the test button results and the load test results highlighted the underlying issue of the missing neutral ground bond. GFCIs work by comparing the current flowing out on the hot conductor with the current flowing back on the neutral conductor. If there is a significant difference between these two currents, it indicates that some current is leaking to ground, which is a ground fault. The GFCI then trips the circuit to prevent electrical shock. The test button on a GFCI breaker simulates a ground fault by creating an imbalance in the current flow. When the test button is pressed, a small amount of current is diverted away from the neutral conductor, creating a difference between the outgoing and incoming currents. This imbalance triggers the GFCI to trip, confirming that the GFCI mechanism is working correctly. However, while load is connected to the circuit and energized, the current flows through the load and returns to the neutral conductor. If there is no actual ground fault, the current flowing out on the hot conductor should be equal to the current flowing back on the neutral conductor. In this case, the GFCI should not trip. The problem in this scenario was that the absence of a neutral ground bond created a situation where the neutral and ground conductors were at different potentials. This potential difference could have been caused by various factors, such as transformer phase shifts, unbalanced loads, or impedance differences in the wiring. When the neutral and ground conductors are at different potentials, it can cause current to flow through the ground conductor, even when there is no actual ground fault. This unintended current flow can interfere with the proper operation of the GFCIs, leading to nuisance tripping or failure to trip when a ground fault actually occurs. Once the neutral was bonded to ground, the potential difference between the neutral and ground conductors was eliminated and the GFCIs started functioning correctly. This demonstrates the critical importance of ensuring that the neutral and ground conductors are properly bonded in electrical systems that use GFCIs. In conclusion, GFCIs rely on current balance to detect ground faults, and the test button on a GFCI breaker simulates a ground fault for testing purposes. A load test, on the other hand, energizes the circuit with a normal load and does not simulate a ground fault. The bond between the neutral and ground conductors is crucial to ensure proper operation of GFCIs and prevent nuisance tripping. Without a proper neutral-ground bond, GFCIs may not function correctly, which can pose a serious safety hazard. Therefore, it is essential to verify that the neutral and ground conductors are properly bonded in any electrical system that uses GFCIs. Firstly, understand the basic principle of GFCI operation. GFCIs work by monitoring the current flowing through the hot and neutral conductors. Secondly, remember that the test button on a GFCI breaker simulates a ground fault by creating an imbalance in the current flow. Thirdly, recognize that a load test energizes the circuit with a normal load and does not simulate a ground fault. Fourthly, appreciate the crucial role of the bond between the neutral and ground conductors in ensuring proper GFCI operation. Fifthly, understand that a missing or inadequate neutral ground bond can lead to nuisance tripping or failure to trip when a ground fault occurs. Sixthly, always verify that the neutral and ground conductors are properly bonded in any electrical system that uses GFCIs. Seventhly, consult with a qualified electrician if you have any questions or concerns about GFCI operation or neutral ground bonding. Eighthly, follow all applicable electrical codes and safety regulations when working with electrical systems. Ninthly, prioritize safety when working with electricity to prevent electrical shock and other hazards. Tenthly, remember that GFCIs are an important safety device, and it is essential to ensure that they are functioning correctly to protect people from electrical shock. The reason the test button trips the GFCI breaker, but a normal load may not even when there is a ground fault, is due to the method of detection. The test button introduces a specific, designed imbalance that the GFCI is calibrated to detect and respond to by tripping the circuit. This is a controlled simulation of a ground fault. When a load is connected, the GFCI still monitors the current balance between the hot and neutral wires. However, a ground fault might not always create a sufficient imbalance to trigger the GFCI, especially if the fault current is low or if there are other factors affecting the current flow. The absence of a proper neutral to ground bond can exacerbate this issue. The neutral to ground bond is essential for providing a low impedance path for fault current to flow back to the source. This low impedance path helps ensure that a significant imbalance occurs, which the GFCI can then detect and respond to. Without this bond, the fault current may take a less direct route, potentially through other grounding paths which may not create a sufficient imbalance to trip the GFCI. This is why bonding the neutral to ground corrected the problem. It established the necessary low impedance path for fault current, enabling the GFCI to function as intended. To further clarify, consider these points. The GFCI breaker's test button introduces a specific amount of current imbalance that is guaranteed to trip the breaker. A real ground fault may not always create the same level of imbalance. The neutral to ground bond provides a dedicated path for fault current to flow back to the source. Without this bond, the fault current may take alternative paths that do not create a sufficient imbalance. The sensitivity of the GFCI breaker is a factor. Some GFCIs may be more sensitive than others and may trip more readily in response to small imbalances. However, even with a sensitive GFCI, the neutral to ground bond is still necessary for reliable operation. The impedance of the ground fault path is crucial. A high impedance ground fault path will limit the amount of fault current it flows, making it less likely that the GFCI will trip. The neutral to ground bond helps reduce the impedance of the ground fault path. The type of load connected to the circuit can also affect the GFCI's operation. Some loads may create more electrical noise or harmonics that can interfere with the GFCI's ability to detect a ground fault. The condition of the wiring in the circuit can also play a role. Damaged or deteriorated wiring can create leakage current that can interfere with the GFCI's operation. Regular testing of GFCI breakers is essential to ensure that they are functioning properly. The test button should be used regularly to verify that the breaker trips when a ground fault is simulated. If a GFCI breaker fails to trip when the test button is pressed, it should be replaced immediately. When troubleshooting GFCI problems, it is important to check the neutral to ground bond. If the bond is missing or inadequate, it should be corrected. It is also important to inspect the wiring in the circuit for any signs of damage or deterioration. If any problems are found, they should be repaired by a qualified electrician. In addition to the neutral to ground bond, other factors can affect the operation of GFCIs, such as voltage fluctuations, electromagnetic interference, and temperature changes. It is important to consider these factors when troubleshooting GFCI problems. The location of the GFCI can also be a factor. GFCIs that are installed in damp or wet locations are more susceptible to failure. It is important to protect GFCIs from moisture to ensure their reliable operation. The age of the GFCI can also affect its performance. GFCIs can degrade over time and their sensitivity may decrease. It is recommended to replace GFCIs every 10 to 15 years or sooner if they show signs of malfunction. Finally, it is important to remember that GFCIs are not a substitute for proper grounding. GFCIs are designed to protect people from electrical shock, but they do not prevent equipment damage or fire hazards. Proper grounding is still necessary to protect equipment and prevent fires. The essential function of a GFCI is to protect individuals from electrical shock. It does this by constantly monitoring the balance of current between the hot and neutral conductors. In a properly functioning circuit, the current flowing out on the hot wire should equal the current returning on the neutral wire. If there is a difference, it indicates that some current is taking an unintended path, such as through a person's body to ground. GFCIs are designed to detect even very small imbalances in current, typically on the order of 5 milliamps. When an imbalance is detected, the GFCI trips the circuit within milliseconds, cutting off the flow of electricity and preventing a potentially fatal shock. The test button on a GFCI is a convenient way to verify that the device is functioning correctly. However, it is important to understand that the test button only simulates a ground fault. It does not test the GFCI's ability to detect a real ground fault under all conditions. A real ground fault can occur due to a variety of factors such as damaged insulation, loose connections, or water intrusion. The severity of the ground fault can also vary, depending on the resistance of the path to ground. In some cases, a ground fault may create a significant imbalance in current, which the GFCI will detect and respond to quickly. In other cases, the imbalance may be smaller and the GFCI may take longer to trip. The absence of a proper neutral to ground bond can significantly affect the GFCI's ability to detect and respond to ground faults. Without this bond, the fault current may not have a clear path back to the source, and the resulting imbalance may be too small to trigger the GFCI. This is why it is so important to ensure that the neutral to ground bond is properly installed and maintained. The neutral to ground bond is typically located at the service entrance, where the electrical service enters the building. It consists of a connection between the neutral conductor and the grounding electrode system, which is typically a metal rod driven into the earth. The purpose of the grounding electrode system is to provide a low impedance path for fault current to flow back to the source. This low impedance path helps ensure that a significant imbalance occurs, which the GFCI can then detect and respond to. In addition to the neutral to ground bond, other grounding conductors are also used throughout the electrical system. These grounding conductors are connected to the metal enclosures of electrical equipment, such as appliances, lighting fixtures, and panels. The purpose of these grounding conductors is to provide a safe path for fault current to flow back to the source in the event of a fault. If a fault occurs, the fault current will flow through the grounding conductor back to the source, tripping the circuit breaker and cutting off the flow of electricity. This helps prevent electrical shock and fire hazards. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are safe and reliable. It is important to follow the NEC requirements when installing and maintaining electrical systems. Article 250.4a of the National Electrical Code (NEC) covers grounded systems. Grounded systems shall be grounded in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that will stabilize the voltage to ground during normal operation. Article 250.24 of the NEC covers grounding service-supplied alternating current systems. For a grounded system, a grounding electrode conductor shall be used to connect both the grounded conductor and the equipment grounding conductors to the grounding electrode. For an ungrounded system, an equipment grounding conductor shall be used to connect the equipment grounding conductors and the grounding electrode. Article 250.50 of the NEC covers grounding electrode system installation. All grounding electrodes as described in 250.52 that are present at each building or structure served shall be bonded together to form the grounding electrode system. Where the system grounding electrode connection is made at the service, the required bonding jumper shall be used to connect the grounding electrodes together. The grounding electrode conductor is used to connect the system grounded conductor or the equipment to a grounding electrode or to a point in the grounding electrode system. The grounding electrode conductor must be sized according to NEC Table 250.66. The equipment grounding conductor is a conductive path designed to provide a low impedance ground fault current path to the electrical supply source and facilitate the operation of overcurrent protection devices. Equipment grounding conductors must be sized according to NEC Table 250.122. Remember that safety is paramount when working with electricity. Always take precautions to avoid electrical shock and fire hazards. If you are not comfortable working with electricity, it is best to hire a qualified electrician.